So induction and energy transfer. So here in this figure, it's shown that a rectangular loop of wire of width L. So this is the width and has one end in a uniform external magnetic field that is direct perpendicularly into the plane of the loop. So this is the external B field, and so part of the loop is inside the magnetic field. This field may be produced by a large electromagnet. The dashed line in the figure shows the assumed limit of the magnetic field. So this there is something like a boundary. So inside this this area, there are some uniform B field, and outside the loop there are nothing. So the fringing of the field at its edge is neglected. You are to pull this loop to the right at a constant velocity v. So you try to drag the loop to the right. So from the magnetic flux point of view, of course, when this loop is moving to the right, the magnetic flux is decreasing because it is something like B times this area, and if this loop is moving to the right, the area becomes smaller and smaller. The rate of work done, so you need to pull this loop to the right with the velocity v, and there is a force. Actually, there will be a force try to pull it from you. We try to pull it to the right, but actually the magnetic field will try to forbid you to do so, although it fails to forbid you. But there is a force acting to the left because suppose there is okay, let me continue this part first. So the rate of work will be the force times the moving velocity. It is something like FA. Okay, so the work done by you will be something like W equals Fs. Fs is the displacement, and P will be something like the derivative of the work done with respect to time. So it is something like this, because the F should be a constant. So it will be nothing but P equals Fv. Okay, so let's come back. We'll try to know what is the force, what will be the work done here. So let's consider the magnetic flux. The magnetic flux across this loop is because it is uniform, so it's nothing but the magnetic field multiply the area. The area is L times X. So according to the Faraday's law, assume we neglect the direction first, so we just ignore the minus sign of the right hand side. So we have the electromotive force equals to the derivative of the magnetic flux with respect to time. So we have like this, and we substitute phi b into here, and B and L will be a constant to time. So so the only term inside is x. So dx dt is nothing but the velocity. So there will be an induced electromotive force. As much as this. Okay, so we have electromotive force. And next, due to this induced electromotive force, um, and suppose we have a collective resistance R, although a conductor line have a very low resistance, but it's not negligible in here because if it is if the collective resistance is zero, so the current will be infinitely large, so it doesn't make sense. So we assume the total resistance around this loop is R, and so we can apply I equals the E, or you can consider it's a voltage divided by the resistance. It's just a Ohm's law. So in the last page, we have E equals to BLV. So we substitute it here to get the current, something like this. And actually, in chapter 28, you know that if current moving inside the magnetic field, there will be a force acting on it, and it's actually the Lorentz force to the wire. So we know that the B field is only this area, so there's no force acting on this line. And for this one, the current is going to the right, and the magnetic field is into the page. So we use the right hand rule. The force will be direct to the direct upwards, and similarly, if the current is clockwise, and so the direction of this line is to the left. So to the left, and the magnetic field is into the page. So we use the right hand rule. So the force is pointing to the downside. So these two forces cancel with each other. So they cancel each other. And the remaining force is this one, the F1. F1 is something like the current is going upward. So upward. So we use the right hand rule. The force should be turning to the should be point to the right, to the left. F1 should turn to the point to the left. Okay. So before that, how do we determine the current is going clockwise? So actually, suppose we pulling the loop to the right, the magnetic flux go across this loop is decreasing. So this loop will try to have an induced magnetic field, so that to slow down this changing. And so the induced magnetic field should be pointing inside, because originally the B field is going inside, and you try to move this loop to the right, and it is decreasing. So it will try to induce a magnetic field pointing into the page. In this case, using the right-hand rule, the current of this induced current should be clockwise. So next, we know that the force will be ILB and sine 90 degree because they are perpendicular to each other. And so it's nothing but ILB. And here we know that I is BLV over R. So we substitute it here. And it turns out F will be something like this, B squared L squared times V over R. And BLV are constant, and speed at which you move the loop is also constant. If the magnitude of force you apply to the loop is also constant. So all the terms are constant, so the force is also constant. And in this case, we know that P equals Fv, so the power of it will be like this: B squared L squared V squared over R. The work that you do in pulling the loop through the magnetic field appears thermal energy in the loop. So you will try to dissipate some power if you really drag this loop. So here, this talks about the eddy current， 就是一个涡状的电流。So in the previous page, we have an explicit loop here, so that the current will, of course, follow the wire to go. You cannot go in another path. But here, suppose you have a conducting plate, and you try to drag it out from the magnetic field. It will also generate an eddy current. It's said that the eddy current are induced in the plate. A typical loop of eddy current is shown. So the loop would be something like this. There's not an explicit loop there, but there will be some eddy current in this plate, so that it will consume the power of the magnetic field. Okay, so using the induced electric field, we can write the Faraday's law in its most general form. Originally, on the left hand side is E, the induced electromotive force, but here we write it as a line integral, similar to the Ampere's law. So this is actually a linear, a line integral, and the right side is the same as before. So actually, you know that the electromotive force is the E field going through a loop. The loop may be can be defined by you, and you just follow this loop and you work on the E field in the product with the infinite testing mode length, and you sum up all the terms, and you will become an integral, a line integral. So here, changing magnetic field produce an E field. So here shows this graph. It shows suppose in this yellow region there is a magnetic field, and this magnetic field is changing. So according to Faraday's law, we know that there will be an E field also generated across this loop. So actually the E field will be something like this. At this point, the E field is pointing upward. This point is pointing to the left. This is pointing down. This is pointing to the right. And actually, for this loop, suppose this loop is assumed to be counterclockwise. So the direction of the E field is actually the tangent line to this circle. And actually, suppose the B field is a circle, so you can determine many E field lines, and according to what we mentioned in chapter 22, the E field line is, which is more dense, the E field will be larger, and for this part, the E field is weaker. And here is mentioned that induced E field are produced not by static charges, but by a changing magnetic flux. So if the B field there is static, then there is no induced electric field. Only is the induced electric field only exists due to the changing magnetic field, so that the magnetic flux across any loop is changing, so that the derivative of the magnetic flux is not zero, then you can get a non-zero line integral for the left-hand side, and thus there will be some induced E field. Electric potential has meaning only for electric fields that are produced by static charges. It has no meaning for electric fields that are produced by induction, because you cannot use the idea of electric potential. Because when you have a circuit, something like when you run the circuit analysis, you have something like something like this. You have a battery. We write it like V, and suppose this is a ground, and this is R1, R2. So actually, this is ground, so the voltage here is 0, and this is V, and this one will be a little bit lower, V prime, and we assume the current I will be something like R1, R2, V, something like this, and V prime will be V minus IR1. So this is very simple. So you can suppose I just expand it. So it will something like, so we have V, this is V, and this is V1 and 0. So actually this is just pass through the R1. This is due to the R2. So we have a voltage drop, and here we have a voltage jump due to the battery. However, here, suppose this one is not 0. So it's not 0. If you still consider it as a voltage, it will be very strange, because it's something like the voltage is going in this direction, is going down. However, when you go for a loop, you go to the original place. So it's just like in a building, you try to go downstairs. And suddenly you find that you go to the original point. This doesn't make sense. So in this case, you cannot consider electric potential when there are time varying magnetic field. So here it talks about if the magnetic field increase at steady rate, a constant induced current appear in the copper ring of radius r. So it's just a simple Faraday's law. And induced E field exists even when the ring is removed. Even when the ring is removed. Which means even it is a even there is not an explicit ring, there will be an electric field there. And complete picture of the induced E field displays at the field line. I just mentioned it in the previous slide. And you can see that for similar closed path that's in closed identity area. So for path 1 is here, path 2 is here. So we lie entirely within the region of changing magnetic field. A smaller EMF is induced around path 3. So the induced EMF for path A and path 1 and path 2 are the same. However, for path 3, so part of this loop is outside the magnetic field, so the changing part will also be smaller. So the induced EMF for path 3 is smaller. And for path 4, this loop is totally out of the magnetic field. So there is no magnetic field, no induced EMF for the fourth loop. Loops is related by okay. So any question for this? So let me ask you a question. Why is the induced E field stronger near the edge and weaker near the center? Yes, it's because it's very simple. So because in this page we assume that the B has a static rate of change is a constant. How do I denote it? B. Well, okay, it's fine. Actually, we concern is the magnetic flux here. And actually, we concern about the rate of change of the magnetic flux. And suppose this one is a constant, so it is nothing but this. It's nothing but this. And dB dt is a constant. So actually, of course, this is the electromotive force, and dB dt is constant. So when the area is larger, the induced electromotive force is also larger, which is this term. So near the edge, the E field will be stronger, and near the center, the E field is weaker. So let's have a sample example. Oh, hmm, hmm, hmm. Yeah, you're right, but um, A is proportional to R squared, but S is proportional to R, is 2 pi R. That is pi R squared. So this will increase, this one will increase faster. A will increase faster than S. So near the edge, it will be there will be a stronger induced E field. So for this problem in the figure, take R equals to 8.5 centimeter. dB dt is 0.13 Tesla per second. Find an expression for the magnitude E of the induced E field at point within the magnetic field and radius R from the center of the magnetic field. Evaluate the expression for R equals 5.2. Okay. So we can write E dot ds is just E would be a constant because it is totally symmetric. So it is nothing but E times the integral of ds, so it is just E times 2 pi r, 2 pi r. And phi b will be dA, which is E pi r squared. And so we take the derivative of phi b with respect to the time. So pi r squared is constant to the time. So it is pi r squared dB dt. So it is nothing but 0.13 pi r squared. And we know that E dot ds equals minus d phi b dt. According to the Faraday's law, so we have E 2 pi r equals 0.13 pi r squared. So it turns out E, the magnitude of E will be nothing but 0.065 R. 0.065 R. The unit will be V over M. So we substitute E for R equals 5.2 centimeter. So it is nothing but 0.065 times 0.052. So the answer is 3.4 millivolt. Because it's asked you about the magnitude. Magnitude is always positive. Magnitude of E. Unless it's asked you about the direction, then you need to determine the direction in some ways. So for part B, find expression for the magnitude E of the induced electric field at point that are outside of the magnetic field at radius r. Evaluate the expression for r equals 12.5 centimeter. So for this time, r is larger than capital R. Capital R is 8.5, so it is around like this. So in this case, d phi b dt will be 0.015 pi r squared. In the previous case, d phi b dt is 0.15 pi small r squared. So for this case, pi capital R squared. Within this circle, there are magnetic flux and of course the change of magnetic flux. But outside there are no magnetic flux. So we use the capital R in part B. So similarly, we can write E 2 pi r equals 0.13 pi r squared. And actually the E will be or the magnitude of E, because other terms are positive. So the magnitude of E will be pi and pi are cancelled, so that it will be something like 0.065 capital R squared over R. Of course, the unit is the same, V over M. So actually, it is proportional to the inverse of the distance. For the previous case, it is proportional to R. For this case, is proportional to 1 over R. So for E at R equals 12.5 centimeter, it will be 0.065 times 0.085 square over 0.125. So the answer is 3.8 millivolt, a bit larger then the pure width. Oh, sorry, it should be millivolt over meter. It should be millivolt over meter. And also for this case, because it's electric field, so it is V over M.